Hello, welcome to Physics 2, Lecture 25.1, Electromagnetic Induction. So, in our previous lectures, we have learned that currents produce magnetic fields, something I will reiterate at the end of this video. So, this tends to beg the question then, can we reverse this and say a magnetic field creates a current? Well, Michael Faraday was actually experimenting with a similar idea in mind. He took a circuit on the left-hand side of an iron ring, so when you close the switch, current flows through this coil and should produce a magnetic field. So he was hoping that a magnetic field would be produced in this iron ring that would then induce a current in this circuit and give us some kind of current. And this is a current meter, also known as an ammeter. So he was looking at this exact thing. He was looking to see if a magnetic field could then go backwards and create a current and get a reading from that. He had an interesting result. The answer was, kind of. What happened was the needle of the current meter did jump very shortly and slightly whenever the switch was being opened or being closed. However, once the circuit was closed, or if it stayed open, either way, there was no current. So he could close the switch, you would get a quick jump on the meter, but then even if current is flowing, you don't have any, if current is flowing in the left-hand circuit, you wouldn't get a reading on the one on the right. So this led him to think that it must have to do with a changing magnetic field that gives you a current, not necessarily a steady one. And so he proceeded then to run through a series of additional experiments to test this idea. And so this lecture is basically us just going over those experiments. So the first thing he did was he placed one coil connected to a battery with a switch directly on top of another. Notice that the other one doesn't have any battery or anything. He was just seeing if we could get a current in this one due to the other circuit. So what he found was that there was no current in that lower circuit while the switch was held open or kept closed. But, again, there was a momentary current that appeared whenever the switch was being opened or being closed. So just for a second, as the switch was being closed or opened, you would get a current. Additionally, this gives us a result of that, or an understanding that opening or closing the switch will create a momentary current. So he then proceeded to take a bar magnet and push it through a coil of wire. So his idea is, if it's a changing magnetic field that's giving us a current, well, you can change a magnetic field, sure, by opening or closing a switch, but why not take a magnet and pass it through the coil? So this is what he did. And what he found was that there was, again, a momentary deflection of your ammeter while the magnet was being moved. But if you held the magnet in place, there was no effect. In other words, once the motion stopped, there was no current. If you then took that magnet and reversed it and pulled it out, you would see again a deflection of the needle, but in the opposite direction. So we are again seeing some hint of this idea that a changing magnetic field can give you a current. So the result of this experiment is that pushing a magnet into or out of the coil will produce a momentary current. Well, who says you have to move the magnet? What if you can take the coil and move that instead? So Faraday did that for his third experiment. In this case, you have a magnet with a north and a south pole, and instead of moving the magnet, this time we're going to move the coil of wire. So in this case, we take the coil of wire and either pull it out really quickly or push it back into the magnetic field. Again, the action of moving it created a momentary current, but if the coil was held stationary in the magnetic field, there was no current. So we again see opposite directions of the needle to whether you're pulling it in or pushing it out. So we have a result, again, that pushing the coil into or out of the magnetic field will produce a momentary current. So we can summarize these ideas. There is a current in a coil of wire if and only if the magnetic field passing through that coil is changing. So in all three of our experiments, it was only when the magnetic field was changing that we saw a current. And we arrived at that in one of three different ways. Opening or closing a switch, pulling a bar magnet out of a coil or pushing it into it, or reversing that and taking the coil and pushing that in or pulling that out of the magnetic field. So the current that we produce in the circuit because of this is induced. In other words, we create it to happen. And so we call this an induced current. The current whenever you have a changing magnetic field making it happen. Now this process has a specific name. So the creation or the process of creating a current by a changing magnetic field is what we call electromagnetic, or EM, induction. So we are inducing an electromagnetic field, and as a result, we create an induced current in the circuit. So these are really, really fascinating results. What I'm going to do now is actually play two videos that I recorded earlier. So it's going to be kind of weird. I'm going to play a video of mine inside a video of mine. But the first thing I'm going to show you is just a recap. This is from our previous material. I just wanted to play this before we get into a really cool demo at the end of this video. So I'll let this play out, and I'll see you on the other side. Alright, so just as a quick reminder, I wanted to emphasize the fact that a current will produce a magnetic field. So what I'll do is simply attach a wire to the two ends of a battery with a magnetic compass underneath it, and we should see if current is flowing, a magnetic field should be produced, and thus we would see the compass needle deflect. So let's take a look. Right now it's pointing roughly north to south, and let's get a current flowing in this wire and see what happens. So there we go, the wire ended up pointing toward the battery, which makes sense by the right-hand rule. If you have current going from the positive end up to the negative end, by the right-hand rule, our fingers should be curling to the left or toward the battery whenever we are underneath the wire. Now, if we wanted to try something on top the wire, we could see what happens there as well, if I can get this to work. Now we're on top the battery, and take a look at that. Now it deflects to the right. So when we're on top the battery, or on top of the wire, our fingers are curling around and back to the right. So this is just a very simple demonstration revealing that, of course, we see current producing a magnetic field. Okay, so that was just a recap showing us that currents produce magnetic fields. The reason I'm showing you that is because the next video is a little bit more involved. So here I'm going to play a really cool video for you. I'm just going to let it play out and then we'll kind of discuss it once more at the end. So please watch this one. This one's very, very cool. I think so. What we've just learned about is absolutely incredible, and you might not have a sense for that yet, but I'm going to perform one experiment before we get into the deeper material to suggest how really fascinating this material can be. This device, as you can see, is named a ring launcher. You don't see any ring yet, but looking at this device, all we have here is a coil of wire wrapped around a metal rod. That's it. There's no physical moving parts, nothing moves up or down, left or right. All it is a coil of wire that if I hit this switch, current will move through. So what's so cool about this? Well, I'm going to bring in a ring. Here we have a hollow cylinder made out of metal, and I'm going to place this on top of the ring launcher. Let's see what happens if I flip the switch. Good Lord. Okay, so let me find where that went. No, I think it's gone. So we saw, without any physical moving parts, a metal ring fly up into the air. This is incredible to think about. I mean, we didn't physically move anything. So what happened? Well, the short answer is electromagnetic induction. We established a current in this coil. What's interesting, though, is we're using an AC outlet, an outlet from the wall. What you might not know is that AC current flips back and forth 60 times a second. So we have a constantly changing magnetic field. Well, we just learned that if you have a changing magnetic field, that you will induce a current. So what we did is we induced a current in that cylinder. We forced a current to form inside of the cylinder. Now, because a current was moving in the cylinder, it created its own magnetic field, like we learned about in our previous lectures. Currents produce magnetic fields. So in a very basic sense, what just happened was it completely produced a magnetic field that opposed the magnetic field of the coil, and once those magnetic fields opposed, you have opposing forces, and it goes flying off. So let me repeat this one more time. Let's see what happens if I hit the switch, and nothing's happening. Well, what just happened? We just did the same thing, but something is different. This time, I used a cylinder with a strip cut out of it. In other words, we don't have a complete loop anymore. In other words, a current cannot flow through this. So that kind of proves our point, that a current must have been induced so that the current could spin around this cylinder and create its own magnetic field. But if you cut off the ability for it to create a current, we didn't see anything happen. So we induced a current in the cylinder, it produced its own magnetic field that opposed the other, and it went flying up into the air. To show you one more demo, I'm going to use this here. This is also a coil of wire. You just can't really see it. It's underneath this casing, and it's connected to a light bulb. And so in this case, I'm just going to use this idea to light up a light bulb without physically touching this to anything. We're going to make this light bulb light up basically through air. I should have figured out how I'm going to hold my phone for this. Well, let's see. How can I do this? I can't leave it on there. So, sorry guys, 1 second. Maybe I can hold it up against this. Okay, that kind of works. So, what I'm going to do is hold the switch down so that the current is moving, and I'm just going to slide this down over the rod and see the light bulb light up. I'm not going to physically touch it at all. And there we go. I'm lighting up a light bulb through air. So, this is one of the really cool experiments that can be done to show an example of electromagnetic induction. All right, so hopefully you found that interesting. This is a really, really cool result. And so let's just kind of recap this one more time. Our definition for inducing a current is that it happens if and only if the magnetic field passing through the coil is changing. So in these demos, we had a coil or a loop. I'll use the light bulb as an example. So here, if I hold the switch down, we're connected to an AC outlet, which means alternating current. So the current flips directions back and forth 60 times a second. So it's producing a changing magnetic field around this loop of wire, which means there is a changing magnetic field in the loop of this current here, or in this loop of wire here. And because of our definition, if you have a changing magnetic field there, it's going to induce a current in this coil. That current will then run through the light bulb and illuminate it. And so we see pretty interesting results because of this. Now, my definition of why the ring flew up into the air, or my explanation, involved opposing magnetic fields. That's kind of a very basic view or explanation of it. There is a lot more behind this than we know at this time. But I wanted to show this early on to get you interested in this material. So that's it for this lecture. After this, we'll start getting into some of the really fascinating stuff that kind of operates in the background of all of this. So thanks for watching, and have a great day.